So, p-values, what exactly are they? Well, a p-value is the probability of obtaining test results at least as extreme as the result actually observed under the assumption that the null hypothesis is correct. Now, it's one thing to say this, but to actually understand it, we would need an example. So, imagine this scenario. Rama is the owner of a Minecraft server with his friends. One day, Rama finds that Filbert somehow has a ridiculously large amount of diamonds in his inventory. Rama accuses Filbert of using wall hacks to instantly find diamonds. Filbert argues that he just got really lucky while mining, and he says that Rama can't actually prove anything. Not sure what to do, Rama turns to you, a data science major at UCSD. Now, luckily for Rama, you just learned this in DSE 10, so you devise a hypothesis test. You know that the chance of finding diamonds in the current version of Minecraft is 0.2% chance for every block you mine. You also know that Filbert got 50 diamonds out of the 10,000 blocks he mined last night. Your null hypothesis is that Filbert managed to mine 50 diamonds last night by luck. Or in other words, he did have a fair 0.2% chance of getting a diamond per block, but he just got really lucky last night. Alternatively, your hypothesis is that there were external forces that enabled Filbert to get 50 diamonds last night, probably cheating. Or in other words, his chances of getting a diamond were higher because he used wall hacks. Higher than 0.2%, that is. Our test statistic will be the amount of diamonds mined in 10,000 blocks. So we're not gonna focus too much on the code here, but you do your thing. You generate 100,000 simulations of Filbert mining 10,000 blocks, each simulation giving you the total amount of diamonds he mined in that simulation, with a 0.2% chance per block to find diamonds. And what I want you to notice here is that that's the null. That's what we mean when in the definition of the p-value we say under the assumption that the null hypothesis is correct. So what we're doing here is we're generating a bunch of simulations, all of them under the assumption that there is indeed a 0.2% chance per block to find diamonds. So yeah, we're just generating a bunch of simulations under the null hypothesis. So let's just say, for example, our test results, our results look something like this. And it's very important that you know how to read this graph. It's basically saying like the amount of simulations in which we got 20 diamonds is this amount of times. The amount of simulations where we got, for example, 5 diamonds is like this amount of times. The amount of simulations where we got around 50 diamonds is this amount of times. Now, how do we calculate the p-value from this? Well, usually we do something with like np.count non-zeros, right? But what does this actually mean? Now, I want you to recall the definition of the null hypothesis again. It is the probability of obtaining test results at least as extreme as the result actually observed. Now, what's the result actually observed? It's 50, right? So, what are the test results that are at least as extreme as the result actually observed? It would be all of the test results that are above 50, that are at that are as extreme as 50 or more extreme than 50. So it's just everything above 50. So let's just shade that region here. So this is the amount of times we got a test result at least as extreme as the result actually observed. Now, how do we count the probability of us getting this? Well, simple. It's just we the amount of times we got more than 50 diamonds, the amount of simulations we did where we got more than 50 diamonds, divided by the total amount of simulations we did. And by doing that, we get the probability of us getting more than 50 diamonds in our simulations. So that's where np.count simulated stat is more than observed stat comes in. That's the blue shaded region here. That's basically us counting the amount of times where our simulated statistic is more than the observed statistic, and then we divide that by the amount of simulations we have overall, or 100,000. And that's how we get the p-value. So it turns out that in our actual scenario, the p-value is 0 here. And what does it exactly mean when our p-value is 0? It means the probability of obtaining test results at least as extreme as the result actually observed, under the assumption that the null hypothesis is correct, is 0. The probability is 0. In other words, the probability of Filbert getting 50 or more diamonds if he didn't cheat, if he did actually have a 0.2% chance, is 0. So for Filbert to have gotten 50 diamonds, he was either really, really lucky or just cheating. So that's why when we say we reject the null hypothesis when the p-value is below 0.05, we are basically saying that since it is very unlikely that the thing we observed happens under the null hypothesis, less than 5% chance, the null hypothesis is probably untrue. So since it is very unlikely under the null hypothesis that Filbert gets 50 or more diamonds, then the null hypothesis is probably untrue. So to recap, what is a p-value? Well, a p-value is, again, the probability of obtaining test results at least as extreme as the result actually observed, under the assumption that the null hypothesis is correct. How do I typically calculate it in DSE 10? Well, we do it by getting the amount of simulations that got a result as or more extreme than the observed statistic, and we divide that by the total amount of simulations we did overall. Now, here are some extra thought exercises, and if you actually did understand p-values, and you should be able to do these exercises. Now, what if we did more simulations? Would the p-value increase, decrease, or would it stay the same? Or do we need more information? Pause the video to think about it for a second, and we'll get to the answer in a bit. Okay, so the answer is that it's actually possible for the p-value to increase, but it's also possible that the p-value would stay the same. When we do more simulations, it is possible that in one of our simulations, we get like extremely super duper lucky, so that even with a 0.2% chance, we get like more than 50 diamonds. Like, that's just a possibility. So it's possible that the p-value could increase. But it's also possible that, we don't get lucky and all of the simulations we do are still just below 50 diamonds, in which case, well, the p-value would stay the same. Now, what's for sure is that the p-value won't decrease because, well, the p-value is already 0. It can't get any lower than that. So, extra thought exercise number 2. What if last night Filbert mined 25 diamonds instead? Would the p-value increase, decrease, stay the same, or do we need more information? Again, pause the video to think about it. Alright, so the answer is that the p-value would actually increase. So first, what happens is that the observed statistic decreases from 50 to 25, so we just move that over here. And now suddenly, there are more simulations where we got a result at least as extreme as the observed statistics. There are more simulations where we got more than 25 diamonds. And because of that, the p-value increases. And this is the last thought exercise. So let's just imagine a different scenario. After the whole Filbert incident, Rama decides to go mining, and he mined 10,000 blocks, and out of all those blocks, he got 10 diamonds. This is way less than he expected, and Rama suspects it is because Filbert already mined all the diamonds in the area with his wall hacks. But Filbert says it is a skill issue, and Rama's just unlucky. Again, you devise hypothesis test. This time your null hypothesis is that Rama had a fair 0.2% chance of getting a diamond per block, but he just got unlucky this time. And your alternative hypothesis is that Rama's chances of getting a diamond was lower than 0.2% because of external forces, which is that Filbert already mined all of them. And your statistic will be the same. It's the amount of diamonds mined in 10,000 blocks. So, how do you calculate the p-value in this scenario? Again, pause the video, think about it. So, the way we count the p-value is not quite the same as before. Instead of calculating the amount of times we got a simulation where we get more than the observed statistic, we count the amount of times where we get a simulation that whose results are less than the observed statistic. Because okay, that's why in our definition of p-value we use the words at least as extreme as. We don't say at least as large as or at least as small as. We say at least as extreme as. And if that extreme is supposed to be larger or smaller, ultimately depends on the null and alternative hypothesis. So over here, our alternative hypothesis is saying that Rama's chances of getting a diamond was lower than 0.2%. So what we want in our p-value would be something like, what are the chances that Rama gets 10 or less diamonds, assuming that he still has a fair 0.2% chance. So to count the amount of times he got 10 or less diamonds, of course we would need to use less or equal than. And then of course we divide that count by the total amount of simulations we did overall, and then there we go. We have a new p-value. So, p-values. Now you know them. Thanks for watching.